Dear friends, this is our first lecture. We are going to study history of electrical engineering in series of 8 lectures. Here we will discuss how the innovations were taken place from ancient time to Renaissance time up to 17th and 18th century. Most of the electrical research work was done in these 2 centuries. So, how was the life without electricity in ancient times, and how nowadays we are experiencing with electricity? So, the in old ages, middle ages, and Renaissance era, how these developments took place step by step, we will discuss. In ancient times, there was no science. Famous communist philosopher Friedrich Engels wrote that there, there was no any science. That means during this huge period, men only find new phenomena of outward things, collect information about them, and try to explain only by the reflection. So understanding was only on the basis of reflections through the phenomena. This relates completely to the electricity and magnetism discovered in very old times. In old ages, before Christ, we can say, till 5th century AD or New Era, the 5th century. Why 5th century is important? The Western Rome Empire, it was ruined by some invaders. We can say Goth, Hun, and Slovenian tribes. These invaded this Rome Empire and spoiled it completely. And next 1,000 years, Europe was in the dark time of the Middle Age. So in Middle Ages, there was no innovation or nothing was happening. After 1,000 years, Renaissance around 16th and 17th century, when culture and arts in Europe flourished. Below main facts of the electricity and magnetism history, from the magnet and amber discovery till first mighty electrostatic generator will be observed. Means amber discovery, magnet and amber discovery was the first, and eventually it concluded to the electrostatic generator. This was the journey. Now we'll see in details how old ages were there. In these times, first buildings and machines were designed and erected in Egypt, Babylon, Old Greece, and Rome civilization. In construction, huge buildings, public buildings, Egypt pyramids, canals, bridges, irrigation systems, water supply. In navigation, boats and ships, ports, navigation, instruments. In army and military service, cold arms, war chariots, catapults, war machines, and fortresses attack. These equipments were used in army and military service. First science observation and skills were obtained. In astronomy, observations of sun, moon, and other planets to forecast floods, eclipses, may be man-fate astrology. So in astrology also, these people were advancing. In geometry, tools to land, measure, and sharing building erections. So for building erection, geometry was in use. In medicines, some medical treatment tools were used. Very important finding were written languages. So scripts were being developed in this era. And accounting skills, but usually it was a secret priest knowledge. employed for divine service. So accounting also was the subject these people learning. In these old ages, 6th to 3rd century before Christ, were created foundations of geometry, Pythagoras, Euclides, mechanics, Archimedes, and atomicists, Democritus. The latter claimed that everything consists of atoms and emptiness, for which he was highly valued by the Marxists. A special role was played by the creation of the 4th centuries before Christ. The first scientific school called Academy was founded by the first idealist philosopher Plato. This Plato was the first person to find the academy in 4th century before Christ. But in India, there were also some Takshashila, Nalanda University. These universities were international universities run in India also. The tyrant Dionysius sold him into slavery to a certain merchant, Anicetus, who, upon learning that Plato was a philosopher, set him free. But then Plato's friends collected money for Anicetus as a ransom, but he handed it over to Plato. With this money, Plato has bought a piece of land in Athens, on the site where the mythological hero Academ was supposedly buried, and here he founded his academy. Above the entrance to which was written, "Let those who do not know geometry not enter here." Just the title was given there. Those who don't know geometry should not come here. So Plato started first academy in Europe, in Athens. The most famous Plato Academy apprentice was Aristotle. The students from his academy, Aristotle, the tutor of Alexander the Great of Macedon, who has summoned major ancient science in two books, Physics about the nature and Metaphysics, theories and philosophies. These books were preserved through the Middle Ages because of the Christ Church discovered in them and some reasonable evidences for the Bible. For example, geocentric universe. Geocentric universe. However, the only reliable information reliable information about electricity and magnetism was left in 6th century. 6th century before Christ by the philosopher Thales of Miletus, who observed magnets and amber in Greece. It was also called electron. Magnet was named after the curious lodestone discovered in Magnesia region of the Turkey, attracting iron bodies. Thales explained such strange actions by the magnet soul. Amber, after rubbing, can attract light straws and chaffs. The science of ancient Science of ancient was contemplative. No experiments, no experiences, only reflections. To be preoccupied with practical problems was considered a distance for a true philosopher. A young man begging Euclid to become his student asked him what practical use will there be in geometry. He, turning to his slave, said contemptuously, give him 3 obols, small coins. He seek benefit in the geometry. So the questions these people have were unanswered. So these people were not even knowing the application of these findings in geometry also and other things. So same in Middle Ages there was no that much work was done. We will see further. We will see the time periods and findings in short. In 600 before Christ, first known account of charging of amber was observed. So it started with charge. So this is called as a charge time. These people just observed charge during rubbing of one material with other material. We will discuss in detail in next lectures these experiments how these people carried out. Just charge was the observation. In AD 1600, directly after 1000 years gap, amber was termed as a electric. This was done by Gilbert, scientist Gilbert. In 1661, mechanical means of including inducing charge. Here, induced charges were observed. Inducing or induced charge was the concept observed. In 1675, electrostatic repulsion and attraction was observed. So positive charges and negative charges have attractive force and like charges repel each other. In 1729, conduction of electric charge. So induced charges, there are forces between these two charges. Conduction is current philosophy, current phenomena. Current phenomena was observed. Two types of electricity defined. Two types of electricity, it is positive and negative charges. Leaden jar allowed charge storage. So this was the first capacitor developed. In 1746, circuits and currents were defined. In 1751, Benjamin Franklin published theory of electric fluids. So here, storing of the charge, it is like capacitor. Storing of the charge and discharging with controlled current. So this discharging and charging phenomena were observed in this time period. In 1785, electrostatic repulsion of positive and negative charges were defined. Electrostatic. So static electricity is also important branch. Static electricity. This all started with the charge only. In 1800, voltaic pile allowed controlled discharge of the charge particles, superseding electric fluid theory. Voltaic pile allows controlled discharge of charge particles. So controlled discharging was possible in 18th century. So this will lead to the development of the circuits. Most significant discoveries were made in the period of 1819 and 1875. In 1819, link between the currents and magnetic fields were observed. So current and magnetic field were correlated. This link was very important for the electromagnetism. So this led to the electromagnetism, and various machines were found later. In 1820, currents and magnetic fields used to create motion. In 1825, electromagnets developed, allowing stronger magnetic fields. So these electromagnets, we can say this is metallic former and coil is wound over it, and it will be acting as a strong electromagnet. This coil resulted as a reason for the developing strong magnetic field. This coil is responsible for that. In 1826, Ampere's law defines relationship between the magnetic flux and the current. In 1826, Ampere's law defines relationship between magnetic flux and current. So this flux and current, how these were related, it was explained by the Faraday's laws of electromagnetic induction. Whenever the conductor cuts the flux, EMF is induced in it and it will result in a flow of current. In 1827, Ohm's law introduces concept of impedance, voltage is equal to IR, and admittance in the circuit. In 1830, Henry explains self-inductance. Self-inductance is L is equal to N d phi by dt. So this self-inductance is whenever a current is flown through the conductor or coil, a magnetic field is created around it and the flux is flowing around it. Field means flux. Whenever this flux cuts the conductor, another EMF is induced. EMF is induced, which is called as self-induced EMF. And this is in opposite direction to the applied voltage, also called as a back EMF. So in 1831, Faraday's law explains mutual inductance. Mutual inductance in the sense, how we'll discuss this mutual inductance. This is the first coil, this is the core, common path for the flux, and this is the second coil. So this flux will or the field in the primary will result in the induction in the secondary. So this has a mutual inductance between these two coils. In 1835, Gauss's law describes this magnetic and electric flux. This flux is the common, but magnetic flux is different and electric flux is different. Latter holds for the gravitational flux. In 1840, Joule's law explains resistive heating by the currents and contributes to the law of conservation of the energy. So here heating will create losses, that will be the I square R losses, and conductor or the system will experience huge loss and energy loss also, but it will be converted into the another form, heating of the water, heating of the air, whatever it may be applied. But selection of this conductor should be such that it will be economical or more than the losses. Its cost will be less than the losses. Losses shall be limited here. Losses shall not be higher than the cost of the conductor. In 1845, Kirchhoff's voltage and current laws aid circuit analysis. Here also we know better Kirchhoff's current and voltage law. In 1853, Helmholtz published circuit reduction theorem like Norton's theorem, Thevenin's theorem. Why these theorems were introduced? For large power system, complex networks, and to simplify these networks for the power flow calculations, these reduction techniques were used, like number of impedances were replaced by the one impedance. So there may be number of impedances like Z1, Z2, Z3, Z4, which is replaced by the single impedance Z. And sources also n number of sources, but it is also replaced by the single source. Single source and single impedance is the concept. It is only for the purpose of simplification of the calculations for the power system analysis. After 1873, electromagnetic theory condensed into the Maxwell's equations, which predict the electromagnetic nature of the light. So here the finding was electromagnetic nature of the light. So light is in the form of electromagnetic waveform. This led to further findings or innovations like wireless communication. In 1883, Tesla's first attempt to sell the polyphase alternating current idea. Okay, 3-phase 4-wire. This was the new research. In 1887, Hertz confirms that the light is an electromagnetic waveform. So this Tesla's attempt to Maxwell's equation. Maxwell equation was confirmed in Hertz in 1887 that the light is in the form of electromagnetic waveform, which confirm further wireless communication. So next we will discuss the scientists and their roles, how these people observe phenomena and how these so first one is Thales of Miletus. In 600 century before Christ, first known account of charging of amber. This was just observed by the Greek people, and Miletus just kept the record. In ancient Greek, observed as early in 600 before Christ, that when amber is rubbed vigorously against the cloth or wool, it becomes charged, attracting other particular materials. This is drawn from the second-hand account of the writings of the mathematician and natural philosopher Thales of Miletus. His time period 630 before Christ to 550 before Christ. Unfortunately, none of his work survives. The charging of amber had to wait around 20 to 100 years before receiving the common name electricity, a derivation of the Greek word for amber, electron. So this was the first finding or the observation written by the Miletus. Second is AD 1600 amber like material was dubbed electric. So new term was given by the William Gilbert to the amber was electric word. So here electric word come into the picture. William Gilbert also discovered that earth is a giant magnet. He was working as a court physician to the Queen Elizabeth. So what he did, he published treatise on magnetism. So he was researching the magnetism, demagnete. For this work he investigated other materials that could be charged in the same manner as a amber. To describe this effect he coined the term electric, meaning like amber. In the 150 years following Gilbert's investigation, although a series of important inventions and observations were made, little progress was made towards the understanding of the nature of the electricity. So the same was going on, only understanding the nature of the electricity. Further, 1661, mechanical means of inducing charge. So induced charge, how charge is induced from one metal to other metal was observed, or one material, particular material to the other particular material. Suppose this is a one metallic ball having positive charge, and if we bring some other metallic ball near it, it will induce a negative charge in it, and this was observed by the Gueric. Like also same cloud is there, which is having thunderstorms. It has a positive charge at the bottom of the cloud, and lightning strike is going to create. In this incident, negative charge is induced on the earth surface due to this cloud having a positive charge. This positive charge will result in induction of the negative charge on the surface of the earth. This is the induction observed by this in the 1661. This in the 150 years following Gilbert's investigation, although a series of important inventions and observations were made, little progress was made towards the understanding of the nature of electricity. Here also same efforts were going on to learn, to understand the electricity. Just very slowly these people were learning new things. So fourth will be in 1675, electrostatic repulsion and attraction were observed. So here firstly what this observation was, induction. Induction was observation. Then repulsion and attraction is the secondly these people observed. Robert Boyle is the scientist who concluded that electrostatic repulsion and attraction is there between the charges. So what he observed? He observed that electric force would travel through the vacuum, and the repulsion and attraction of charged objects. In 1733, Charles Francois de Sistine Fay stated that there were two types of electricity. At this stage, the understanding of electricity was still restricted to the charged body, repelling and attraction of objects. So same was going on, no further developments were seen. In 1729, conduction phenomena was observed. Here see how step by step conduction, repulsion and attraction previously, and induction. These are the findings step by step going on. So we have reached up to the conduction phenomena. This was observed by the Stephen Gray. He discovered that electric charge could travel or be conducted through certain materials. Materials could be now classified as being either conductive material called as a conductors and non-conductive materials as a insulator. So current phenomena was observed, we can say the flow of charge, the flow of charge. So further we can see conduction. After conduction, what are the findings? In 1733, two types of electricities were defined. In 1730, Charles this Fay concluded that there is two types of electricity, say positive and negative electricity. So these two different phenomena were found. In 1745, leaden jar allowed to store of charge. So this first condenser or capacitor, we can say, found here. So in 1745, the University of Leiden, Peter van Mozambique, he observed that charge can be stored in the Leiden jar. So he developed device that could allow electrostatic charges to be stored and then discharged. This became known as a Leiden jar. This device was just developed to store the charge. It is now known as the capacitor or condenser. Nowadays, these are used for the power factor improvement. We see. In 1746, circuits and currents were defined. So, this is the circuit. Suppose it has a source, voltage source, it has a resistance, it has a inductance, it has a capacitance. So, these circuits were developed by the William Watson. So, how it developed? Due to the discharged leaden charge through a circuit of a conductive material. So, this battery or capacitor, we say, was discharged through some conductive material, wet thread, and introduced the concept of current. And research further continued for the dielectric materials also, for greater charge storage in the capacitors, and which led to the understanding of the circuits and currents. In 1751, Benjamin Franklin published the theory of electric fluids and kite experiment. In 1751 and 1754, in this period, Benjamin Franklin carried out his work. Kite experiment and Leaden jar experiments we will discuss in further details. More 7 lectures to become for the history of this electrical engineering. He published his experiments and observations on the electricity in 3 volumes. Publications contained first adequate explanation of how Leaden jar worked and introduced his theory of an electric fluid to explain currents in the circuits. He was also attempting to understand the discharging of the Leaden jar. Through this theory, though this theory was deficient in some respects, it was robust enough to allow the other scientists to make great discoveries in following centuries. Many of the terms Franklin introduced in the theory have remained in the use. His work further was carried by Kinnersley. What Kinnersley did? One of the Franklin's collaborator, Ebenezer Kinnersley, dubbed this phase 2 types of electricity as a positive and negative charges. Kinnersley also pointed out that electric fluid theory did not account for repulsion between similarly charged bodies. Electric fluid theory did not account for the repulsion between similarly charged bodies. So, similarly charged bodies are repelled actually for plus same charges, north north, south south, these will repel, positive positive will repel, negative negative will repel, and attraction between the positive and negative. So what he is saying, he pointed out that electric fluid theory did not account for repulsion between similarly charged bodies. So electric fluid theory is just absolute because it is not following the rule of opposition of the same charges. So further, in 1785, electrostatic repulsion of positive and negative charges were defined by Coulomb. Coulomb is a unit of charge. Charge Q is given unit of Coulomb. So this charge or electron has unit of Coulomb, and some charge has a electron, that is formula some 10 raised to minus 19 or like this. We can cross check this, of the electron is stored in the charge. See Coulomb, what Coulomb has done research, he invented torsion balance. So torsion balance is a weight, balance weight, like this equipment. It has a needle at the top. This is the base. This device capable of quantifying the attractive force and electric charges and magnets. Using this device, he published the finding in 1785, explaining principle that governs the attraction and repulsion between the negative and positive electrical charges. This principle was later named Coulomb's law. Coulomb's law, because there Coulomb's law is like, we can say, there is attraction and repulsion forces between the charges. Unit of a charge. Coulomb was named in his honor. The electrical fluid theory could not be fully investigated as the only available charge sources or batteries, as Franklin coined them, were Leyden jar, and they discharged all stored energy in instantaneous burst. So electric fluid theory could not be fully investigated. So this was not investigated because it was discharging was very quick. What was needed was a longer lasting controllable current that could allow more in-depth study. So electrical fluid theory was not working also. Luigi Galvani, what was his research? He tried to convey that there is a animal electricity. In 1791, Galvani stated, as a conclusion of his study during the 1780s, that frogs' legs, which had been preserved in salt water, were the source of animal electricity, a new type of electrical fluid. But this was also declined by Volta, as that frog was twisted or deflected due to the shock that he has connected it to the battery or the source. Further, in 18th century, voltaic pile allowed controlled discharge of charged particles, superseding electric fluid theory. So, controlled discharging of this voltaic pile. This pile, now Leyden jar was replaced by this voltaic pile. Physicist Alessandro Volta In 18th century, he developed the first practical battery. We can say first practical battery was developed by the Volta. First practical battery. Here we can see this battery. Upper is metallic foil, then in between is dielectric foil, again metallic foil. So he developed this battery. Though his friendship with Galvani was aware of animal electricity, their theory prior to the publication and started replicating dissimilar metals, experiments with thread wetted in salt water instead of frog legs. In the late 1780s, Volta tried to dissuade Galvani from publishing his theory, stating that the diseased dog's nerves disease frogs nerves reacting to the current that caused twitching. His advice having been ignored, Volta set himself to the categorically disapproving Galvani. So these dead frog nerves reacted due to the fault. Again, Volta proved his theory correct with an experiment. A current was carried through wet thread between two cups of salt water with different types of metals in each. So discharging was the objective, discharging of the voltaic pile. So how we try to discharge the theory correct with the experiment. A current was carried by, see, current was carried through a wet thread between two cups of salt water with different types of metals. So this discharging was through the wet thread between two cups of salt water. He had developed first practical battery consisting of vertical stacks of couples of copper and zinc discs separated by the disc of cloth moistened in the salt water. The design is known as a voltaic pile. Publicly demonstrated in 1801, the voltaic pile did not build up as much charge as some Leyden jar, but it could release the charge in the controlled continuous current instead of single burst. So this discharging was possible in controlled manner. The controlled current was the catalyst of electromagnets and the great advances in the electromagnetic theory during the 19th century. The electric potential unit, the volt, was named after the volta, as is the instrument for the measurement of electrical potential, the voltmeter. So voltmeter was named after volta and unit volt to the voltage was given after volta, name volta. So he was honored here. In 1819, link between the currents and magnetic fields was observed by the Oersted. So how he observed? Oersted, what he did? Discovered the relationship between electric currents and magnetic fields. So this was also further led to the Faraday's law of electromagnetic induction. So there is also a magnetic field and electric current relations were confirmed. In 1825, electromagnets developed allowing stronger magnetic field. This was done by William Sturgeon. Also, this Faraday's laws of electromagnetic induction we have to discuss. Suppose there is a magnetic bar with N and S poles, and this is a current carrying conductor with just normally moving near and forth and back to near the magnet, and EMF will induce in this conductor, and which will result in the flow of current. So this is a Faraday's law of electromagnetic induction. Condition is that one of the two, means one magnet and conductor, one should be stationary and one should be in the motion, and then it will cut the flux, which will lead to generation of the EMF. The first systematic experimentation and study of electromagnetism shortly after Oersted published his findings. By 1820, Faraday had demonstrated how currents and magnetic fields could be used for creation of the motion. So Faraday's law of electromagnetic induction was studied. Then Faraday's laws were responsible for the further inventions in the electrical machines. So stronger electromagnets was the need of the hour. Here we have to build larger machines. So he found the strong electromagnet, like this is a metallic arm and coil is wound over it, and this coil is responsible for the building of the stronger magnetic field. He showed that winding a current carrying wire around the iron bar, concentrated magnetic field were generated. Electromagnets allowed the induction of the magnetic fields that were much stronger than those occurring naturally in the lodestones. So lodestone were not used for the manufacturing of the machines in future. So in next, Joseph Henry. He continued to experiment with the electromagnets. So Henry is a unit of inductance. Inductance is the phenomena L is equal to N d phi by dt. So he continued experiment with the electromagnets and discovered self-induction of the circuit in the 1830s. Self-induction explains the operation of the inductor circuit element. The unit of inductance, Henry, was named after him. Henry also observed mutual inductance. Mutual inductance also he was observing at that time. One circuit inducing magnetic field in the other. Transformer is the good example of this during 1830s, but he did not publish his finding. See, this is a coil and current is flowing through it. There is a magnetic field or flux around the current carrying conductor. This flux will cut the conductor. Flux cut conductor. And then EMF, self-induced EMF is generated in this coil, and it will be in opposite direction to the applied voltage, which is called as a back EMF also. So this EMF is due to the inductance, self-inductance, and which will oppose the change in the current. In 1826, Ampere law defined relationship between the magnetic flux and current. Andre Ampere, what he did, this Ampere, he formulated mathematical relationship between the magnetic flux phi and current. So current and flux is directly proportional to each other in DC machines and transformer. This all we have observed or we are studying in engineering subjects. It was published in 1826, book Theory the Phenomena, Electrodynamics, Theory of Electrodynamics Phenomena. Ampere also showed that parallel conductors will either attract or repel each other depending on the direction of the current flows, and invented the static needle also and galvanometer, the devices that measure the current. The unit of the current is ampere. It is named after him as the galvanometer recognizes Galvani contribution for the understanding of the currents. So these two parallel current carrying conductors experience force on each other. This is a Ferranti effect. Proximity effect. Sorry, proximity effect. Proximity effect we have observed. So any two current carrying conductors nearby will experience forces from others. In 1827, Ohm's law introduces concept of impedance and admittance. So here voltage is equal to current into resistance. The condition is that for this formula to be correct, temperature shall be constant, because the resistance is dependent on the temperature or environmental conditions. We can say physical conditions of the conductor shall be remain same. So Ohm just responsible for this voltage and current relationship formula. Henry and Faraday we have already discussed. This repeated. We will discuss now Lenz's law. Lenz also covers conservation of the energy in electromagnetic induction of the motion. We will discuss in details in the next upcoming lectures. We are just discussing findings or inventions done by these scientists and the time period. So this Lenz was 18th century, 1804 to 1865. In 1835, Gauss laws describes magnetic and electric flux, latter holds for the gravitational flux. He contributed to many fields of mathematics and physics. Of importance to electricity, he presented mathematical relationship between the magnetic and electric flux through surfaces and sources of the charge. The relationship is known as Gauss' law. In recognition of his work, the unit of magnetic induction, the Gauss, is named after him. Gauss' law was later found to hold the gravitational flux. So, electric flux and magnetic flux, between these two, he just magnetic and electric circuits. He just differentiated these two relationship known as Gauss' law. In recognition of his work, unit of magnetic induction, The Gauss is named after him. Magnetic induction. We can have an update that magnetic induction is termed unit of Gauss. What is the unit of Gauss? We can have a knowledge. Gauss law later found to hold gravitational flux. Gauss collaborated with the William Edward Weber. Weber is the unit of flux. In 1830s, for the series of electrical experiments, what experiments he did, we'll discuss. Weber's biggest contribution to the study of electricity was his work towards establishing universal units. His act, he just responsible for the universal units development. He originally had the electrical energy unit named after him, but afterwards it was named after the Coulomb. The Weber now refers to the magnetic flux. Further, in 1840, Joule's law explains resistive heating by the currents and contributes to the law of conservation of the energy. Here is energy conservation means saving of the energy. So here in heaters, very high power losses, that I square R losses are generated. It will be a heating loss. So selection of the conductor is very important here. Selection of conductor, conducting material. It shall be such that the losses should not be higher than the cost of the material. Losses should be less than cost of conductor. Otherwise, this product will be in the loss. He stated in 1840s that heat produced in an electric conductor, all the type of electrical heaters are based on this. This was later named as Joule's law, and the unit of energy, the Joule. Also, 1 watt second is equal to 1 Joule. This is a equivalent unit of Joule, 1 watt second. Also, kWh, kilowatt hour, is the unit of the energy. Further, in 1845, Kirchhoff's voltage and current laws aid to the circuit analysis. So, Kirchhoff's voltage and current laws we are also aware. Suppose this is a node and currents entering and leaving here will result in the summation of 0. All sum will be 0. This I1, I2, I3, I4, I1, I2, I3, I4. This summation of these all currents will be 0. And voltage law, voltage drops. IR is the voltage drop. And across these different circuits, various resistances and various currents, depending on the direction of current, these losses, the voltage drops are to be measured or calculated. Voltage drops. Good. So Kirchhoff's is remembered for his research on the electric currents and the discovery and theoretical analysis of the electromagnetic radiation. In 1857, he published his work on the propagation of electric currents in the conductors. As an undergraduate student in 1845, he published Kirchhoff's voltage law, Kirchhoff's current laws. So Kirchhoff's voltage law will have voltage drops summation, and Kirchhoff's current law will be the summation of the currents in the circuit. The cornerstones of electrical network analysis as extensions of Ohm's law. In the 1850s, he and Robert Bunsen developed spectrum analysis and analysis to categorize the chemical elements. This is some different concept we will discuss in next lectures while discussing the experiments of these scientists. In 1853, Helmholtz reduction of the theorems, Norton theorem and Thevenin theorems. Thevenin theorem, n number of impedances, say Z1, Z2, Z3, Z4, Z1, Z2, Z3, Z4 are replaced by a equivalent single impedance Z, and different voltage sources are also replaced by one source. So this will be the reduction of the circuit, and here we can add load. So this is the Thevenin's theorem. We have to just replace number of impedances by single impedance and sources by a single source. He showed that complex circuits, complex networks could be represented by a voltage source in a series with a single element of impedance equivalent to the impedances of the entire circuit. In this form, the simplified equivalent circuit could easily be analyzed with Ohm's and Kirchhoff's laws. So network analysis, different complex circuits to be simplified. Objective is that solution is easy. So these Norton's and Thevenin's theorem were used to study the complex circuits. In 1873, electromagnetic theory condensed into the Maxwell's equations, which predict the electromagnetic nature of the light. So this is also led to the foundation of the wireless communication, that light is a form of electromagnetic nature. Rediscovered Helmholtz's idea. Theorem is now known as Thevenin's theorem, Thevenin's equivalent circuit. Norton, engineer Bell's lab at United States, rearranged Thevenin's theorem to substitute a voltage source with equivalent current source parallel with the single element impedance. This is known as Norton's theorem, Norton's equivalent circuit. This is related to the Thevenin's theorem. So complex network, these are same, these two topics. And this telegraph, French telegraph, engineered to Emil Thevenin. This was also responsible for the study of electromagnetic nature of light. In 1883, Tesla first attempt to sell the polyphase 3-phase 4-wire system. So research has come up to the 3-phase system now. Nikola Tesla tried to sell the idea of the 3-phase 4-wire polyphase machines like 3-phase machines and distribution scheme. He started working for the European branch Thomas Edison Electric Lighting Company in 1883. He was trying to raise the funds to prototype the polyphase alternating current power system he had designed conceptually. So he tried to sell the polyphase machines. In 1887, Hertz, which is a unit of frequency, we have heard about Hertz, confirms that light is an electromagnetic waveform. So this confirmation led to the foundation of the wireless communication. Wireless communication. Just it is a electromagnetic waveform. Electromagnetic waveform. Experimentally proved Maxwell's theory about the light as the electromagnetic waves to be correct. His further experimental work in the field led to the foundation of a wireless communication. The unit of the frequency of the waveform, including electricity transmission, is named as a hertz in his honor. So we will discuss how the experiment confirms the electromagnetic nature of the waveform in the next lectures. So this experiment will be important to confirm light is a form of electromagnetic waveform. So up to this we have discussed many experiments carried out by the scientists in very brief. Now further we have to discuss the experiments, how these experiments were carried out. We have to discuss in details in further next part 1, part 2, part 3, part 4, part 7. Like this. First part we will discuss the old, middle age, renaissance history. This is we have discussed today also, but we'll discuss in details with the conclusion. And in part 2, 18th century electrostatic experiments and first current source creation. Fundamental of electrostatic findings, electrodynamic science origin, Volta's followers, conclusions. In part 3, electromagnetism, discovery and fundamental laws in the first half of the 19th century. Electromagnetic interaction, discovery and research, Ohm's law, experimental findings, mechanical Faraday and his followers, conclusion. Maxwell's electromagnetic theory and its experimental confirmation. James Maxwell main contribution. Maxwell's theory for experimental confirmation. This is electromagnetic theory. This is also electromagnetic discovery and its fundamental laws. Here also electromagnetic theory and experimental confirmation. How Maxwell has carried out further investigation. Electron discovery and its properties estimation. Background of the electron discovery and Thomas and Millikan's experiments. So electron is different than charge. Means charge was the experience and electron was the next finding. Conversion of the electric current into the mechanical motion. This is also we will discuss in part 7. The first experiment in the converting electricity into the mechanical motion. Jacobi's DC motor was there. Jacobi's contribution to the electrical engineering. DC motors and permanent magnets. Reluctance, synchronous and electromagnetic motors. Conclusion. Here in part 7, first electric generator. This is our motto to understand dynamo principle also. The first experiment in the converting mechanical motion into the electricity. Self-excited DC generators and conclusion. These are the topics we will discuss in the next lectures. So I will request you to learn the electrical engineering in details, deep. Please follow this channel and subscribe. We will discuss in depth. You can also ask me questions. So thank you friends. Please go through this lecture and please raise your questions, send your messages. We will try to answer these. Thank you.